All right, everyone. Well, thanks again for showing up today. Almost done. Chapter 13. We're skipping over 12 right now because that's one I always leave till the end. And we're going to start with 13.1, which is all about this thing called sequences and some of the notation. So this first section is going to be a little bit longer than the other two, just kind of setting the stage for the entire chapter. So bear with me. A few little definitions and nuances here. We'll get to it, do a few examples, and we'll move on. All right? So help me out. What is that first blank? A sequence is a blank of numbers whose domain is a subset of the counting numbers, also known as the natural numbers, whole numbers, or what else? Anybody have an idea for that first blank?
Pattern.
Ooh, that's a good one, Anthony.
A set.
Getting warmer. It's actually a list, right? And a set is one way that we say these things, but that's the next little paragraph there. A sequence is just a list of numbers. Okay, and the domain, the input values, are just the counting numbers. And you guys probably know the counting numbers. The first thing you learned how to count was 1, 2, 3. All right, and that's what the natural numbers are called. Whole numbers actually include 0. Every once in a while they'll start at 0, but usually not. These are also called the positive, because we're only going to look at the first, the second, the third of these things, these lists. And those are called the integers. All right, integers actually includes the negatives as well, which is why we have to throw in positive. Okay, the way that we list this set of numbers that somebody mentioned is with these curly braces. All right, so I put in an example here, this curly brace of a list of numbers. Okay, a sequence of numbers. And you guys might even be able to see some patterns with these things, as somebody else also mentioned earlier. Okay, so each number in this list that we're calling a sequence is called a term. All right, so the first term, or the second term, or the 22nd term. We want to be able to list each and every one of these so that we can talk about them. Or what do you think that ... means?
It keeps going on forever.
That's right. It's called an ellipsis, right? But this ... represents that it keeps going on with this pattern and it never ends. Okay? So that's what that ellipsis means, is that that sequence, that pattern, that list keeps going. And we'll denote each and every one of these terms because they can be anything. They used A, and the subscript down here below, N, for any term. So that first one would have been A1, A2, A3, A4, A5. And what we're going to be looking for is that pattern, which is what a lot of mathematics is about, right? Finding patterns of things and how they change. So A1 would have been 1. A2 is 4. A3 is 9, and so on and so forth. And can you see my domain? Or those positive integers, those natural numbers, or what they like to call the counting numbers. So if I input this, I want to figure out how to find any term. We call it the nth term. And can anybody find that general term, they like to call it? The general equation that would give me any one of these things by putting in 1, 2, 3, 4, 5, or whatever? Can you guys see them now that I have them listed right above? Can you see a connection with this to that? This input to that output? input to output for each of these?
Yep.
What is it, Rich?
The input is n, and the well, a in this case, and the output is a squared.
Close. Very good. It's n squared.
Okay, so it wasn't. Okay, got it.
Yes, sir. So this is what we're changing. You see that? The a just represents the term. So when I put in a 1 here, I put it in here, and I get 1 squared, which is that. Put in 2 here and there. 2 squared, which is that. 3 squared, 4 squared, 5 squared. Very good. So if I wanted to know the 10th term, you know right away now it would be what?
100.
That's right. 10 squared or 100. And that's what we're trying to keep it in here. Should have done it in red, right? For all my emoji fans out there. So that's exactly what we're dealing with. Looking for these patterns, and we'll learn when there's specific patterns of these things, we'll give them certain names. All right? So when we have that dot, 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 what kind of sequence or list is that called? Well, that dot, dot, dot means it continues with no end. What thing did we create to represent never ending?
Is it called an infinite sequence?
It is indeed. Very good. Phoning in all the way from the North Pole. That's right. It is called an infinite sequence. So what do you think we call it when it does have an ending term? A non-infinite?
Finite.
Yeah, very good. And you know, infinite is the negating term, right? That prefix. So if we say it's non-infinite, what do we do when we have a negative and a negative in math? They become positive, and therefore we will just have what is called a finite, is how you say it. Okay, a finite or an ending, a certain number. Finite as in finish. All right, we have a finish, an end. Only 10 terms, or 25, or whatever it might be. Okay, and then another term that you will hear, infinite, not infinite, so finite. There's also these called alternating sequences. In alternating, meaning what's going to be true?
The signs alternate?
That's right. So if I wanted to mix it up a little bit right here, and I say, all right, well, I'm going to actually start with a negative and then go positive, then negative, positive, negative. What would I have to change to this formula here that we came up with to find all of these if they're going to alternate from a negative to a positive to a negative to a positive to a negative? What obviously has to be involved? A negative, right? And that -1 is going to be the thing that is going to change these and alternate them. But if I just multiply a -1 times this, what is anything squared always going to give you?
Positive.
Very good. And so every single one of these would therefore then be negative. And we want it to alternate, which means we need to change some stuff. We can't just always have it be negative. So we're going to either have to put an n up here or an n plus 1 or n minus 1, depending on if it's going to start off negative or if it starts off positive and the second thing is negative. And just by doing this, would that take care of the change that I made? Well, put a 1 there. What would it be? Negative. Put a 2 there. Now what is it going to be?
Positive.
And a 3,
Negative.
4. Notice it's alternating for every one of those that we have. Okay, so very good. It's just a matter if we're going to start off negative or if we're going to start off positive, and then the next thing is going to be the negative, whether we're going to just put in or we're going to put in plus or in minus 1 to make it alternate in a different order. Okay, so here's a few definitions here, and then we'll do an example. And again, if you want to take a screenshot of this, or you can watch it back and pause it and write down any of this, you can see the A1, 2, 3, ... to any term. And remember, a finite means it ends. Infinite means it's not finite. It's not finished. It never ends. Right? And what we're going to be looking to do is find what is called the explicit formula, which is what we just came up with to find any of our terms. All right? So if I give you on this first example here, this explicit formula, I'm explaining how to find any term by plugging this in. And what do they want us to do? They want us to find the first 5 terms of the sequence defined by this. So if you want to write it like this with the curly braces around it, that's fine. It's all good. It's totally up to you. All right? I'm not going to nitpick on that, but remember, we're listing this sequence of numbers by putting it in those curly braces and saying this is my set of numbers. And what are we going to do? What are we going to find first? Our steak sauce. We're going to find our steak sauce, A1. All right, then we'll find our second, then our third, then our fourth, then our fifth. And if we can find a pattern from here to here to there, then I don't have to literally go and plug in each and every one of those ins. I can just recognize the pattern and get there a little bit faster. Okay, but what are we going to do to find that first one? To find a in, it's going to be 4 times that n over a -2 raised to that n. So for that very first one, we're going to replace all of those n's with a 1. And that will find a1. So what do we get on top?
4.
And on bottom.
-2.
To give me a final answer for my first term of -2. Always want to simplify it, right? Don't give it to me as this or this. Give me the finished product. Okay, what's the pattern? What are we going to do next? We're going to make all those 2's now to find A2, which means now what are we going to have on top? An 8. Careful. Now what are we going to have on bottom? What is the -2 when you square it?
Positive.
Very good. It is a +4, which gives me a 2. Now, how many terms do we need in order to find a pattern? Can you guys tell me what the pattern is?
At least 3?
Ah, very good, Richard. If I told you that my first one was this and my second one was that, would you know what the third, the fourth, the whatever term is?
Make a pretty good guess.
Okay, what is your guess, Rich?
6?
Nope.
8?
Ah, good, very good. And those are my 2 options, right? The 2 obvious options, I should say. There's many other types of patterns. but am I adding 2 each time, or am I multiplying by 2 each time? You don't know until I gave you this. Then you recognize, all right, well, that's also multiplying by 2, so I would imagine that that pattern continues, and then I can give you the next ones fairly quickly. All right, but we need a third one here, is my point, to see if we can get the other 2 a little bit more quickly. So now I'm going to go over here and I'm going to plug in 3 everywhere, which is going to give me an 12 over a negative 8 in the denominator. Right? Remember, if it's a negative raised to an even, we will have an even number to make that positive. But if there's that one odd one left over, then there's still going to be that negative left. So since it's a negative to an odd, I know it's going to be negative, and then 2, careful, cubed is 8. And of course, what do we want to do before we put that in our answer blank here?
Simplify.
By 4, which would give me that 3 halves negative. Now that doesn't look like a very obvious or nice pattern, so guess what I'm going to do? I'm just going to plug in 4 there, there, and there to get my A4. And then I'll do the same thing for A5, because this doesn't look very good. All right, so I'm going to go ahead and put in a 4 here, which is going to give me
16.
16, very good. And then my negative 2 in parentheses raised to the 4th, which would be positive 16, which obviously is a 1. And then my last step to getting this would be to plug in the 5. And that would give me an answer of what? $20 on top. Negative to an odd, which is 5 here, is going to stay negative. And then 2 to the 5th?
32.
Very good. It's 32. And what can I simplify or reduce 20 and 32 both by?
4.
Very good. 4 goes in that 5 times, and 4 goes in that 8 times. So negative 5/8. Pretty ugly sequence, but wanted to make sure that you guys saw how we got here. And notice when there is a negative raised to a power, what are we going to have? What kind of sequence?
Alternating.
Very good. An alternating sequence. All right. Let's try to work backwards. Let's go back up to my original example that I gave you guys here and see if you then can give me that generic formula to find any of them. So rather than me giving you this and you giving me all of however many terms I want, can you find that formula to move from one to the next to the next? And again, just be careful. I know there's lots of commas going on here, but hopefully you guys can see all of the generic terms. Here's A1, 2, 3, 4 is all of this. 5 is all of that. What do you think? Do you guys see a pattern? What's the obvious pattern that you see right away?
They're alternating.
Good. Positive, negative, positive, negative, positive. I'm assuming the next one would be negative. Excellent. So I know what's going to have to be involved. A negative. Now, do I want that thing to start off negative? Can I just put in up here so that when I put in A1, if I put a 1 right here, notice it would be negative, and we need it to be what?
Positive.
So I have the option of either putting +1 or -1, and that will fix the problem. Because now if I put my 1 in here, now I have a even number, and that will make it the positive that we needed. Okay, and -1 will also work, because we know when we list our numbers 1, 2, and 3, every other one is odd, and every other one is even. So if we just add 1 or subtract 1, that'll take us to the other one that we may need. Okay? But what other pattern do you see is occurring for each one of these?
Powers.
Good, Austin. Austin Powers Faja. No. What are we doing each time? It looks like we're multiplying
Multiplying.
by a 9. That's right.
Hey.
Now, careful with this, because what happens when you add a bunch of times? What did we create? When you take 3 and add it a bunch of times, how could you rewrite that in a much easier form? What do I have?
3 times 5.
So when you have 3 a bunch of times, we literally called it, you have 3 5 times. We created multiplication. Very good. But when we multiplied by the same number a bunch of times, what did we call that? What did we create so that we could rewrite this?
Powers.
Very good. We raised it to the power. So then I know that because this is multiplying by 9 to get 81, and then if I multiply this by 9, that's a 9, and this by 9, I get 72. So I can see that pattern, and I can use my calculator to ensure that this times 9 is indeed that. And this times 9 is indeed that. But we know when we multiply by the same number a bunch of times, we created an exponent. And so if I just changed all of this and I just turned it to be plus signs instead, I make multiplication. Then instead of 3 times 5, we'd rewrite it as 3 to the 5th. Remember, we just worked on exponential functions. Here it comes back into play. I have 3 to the 5th now. Well, how many times am I going to be multiplying by that 9?
5.
So I need 1, 2, 3, 4. I need one more to find the next term, right? You're absolutely right, Richard. But remember, what we're trying to find is for what? The nth term. It's not always going to be the sixth term that we're looking for. It's going to be any number of terms. But notice, how many times would we have multiplied by 9 to get the sixth term?
N plus 1.
Close. How many times did we have to do it to get to the fifth term?
4.
How many times would we have to do it to get to the third term?
2.
One less
Good.
than like the amount of times you actually need to get to there.
Very good. So we would have, sorry, n minus 1 for that 9. And could we just kind of smash these together and just put a negative 9 there? In other words, would this work? We'd have to plug it in and see, right? And let's check. will this give me the first thing that I want if I put in a 1 there? Well, what do I get when I put in a 1 minus 1? And what is anything to the 0 power?
One.
That's no good. I need it to be a 9. So I'm thinking that we're not going to be able to put the minus 1, and we're going to have to leave it like this, even though we saw that pattern. Because how many times are we going to be doing? Any number of times. And we notice when we put in 1, we'd have 1 9. When we put in 2, we'd have 2 9s. Put in 3, we'd have 3 9s. So this looks good. And we had to have the n plus 1 up here to the negative because we wanted to make sure that when we put in our 1, we got an even number up there to get my positive 9. So combining those two together would not necessarily work. And if you ever wanted to be sure that what you put here is correct, use what they gave you and plug in your 1, 2, 3, and 4, your inputs, and make sure that you get out what you should. 100% sure I know I did this right. Okay, so I wanted to give you guys one to try on your own after I kind of talked you through that one. Let's see if you guys can do that second example. Go ahead and give it a shot. I'll pause the recording real quick just to give you guys some time. All right, hopefully you guys had a chance to finish that up. Remember, we're looking for the formula to find any one of these terms. I know that this is my first term, this is my second, third, fourth, fifth. They gave us the first 5 again. Okay, now with this, I need to find a pattern, and I know that it is negative for each and every one of these. So I know that's going to be there. It's not going to alternate, so I don't need anything to a power. But I also know that it's a fraction. And so now I'm going to look, and I'm going to start with the top. And I'm going to look to see, is there a pattern within these? Can I see how it's changing? Just on the top. Then I'll focus on the bottom. How did it move from 3 to a 9? 9 to a 27, 27 to 81, 81 to 243. Did you guys find the pattern?
Multiply by 3.
Good. So just looking up here on the top, the numerator, I can tell that it's multiplying by 3 a certain number of times. How many times? I don't know. It depends on the term itself, right? So how do we write multiplication multiple times?
Powers.
Good. So I will write 3 to the n. And just to check for good measure, when I put in a 1, do I get out a 3? When I put in a 2, would I get out a 9? A 3, a 27, a 4, an 81? Yes. So far, looks good, and the negative is going to be there to get the negative for every single one of those. Details, guys. Make sure you pay attention to that. How about the bottom then? Does this look a little bit easier now? What is the bottom doing to each and every one?
Adding
Add
4.
Multiplying by 4.
Oh, shoot, it's not multiplying by 2. Remember, we said that we need more than just 2 things. We need a third to see it. So very good. It's not doubling like it looked. You guys all said it. Yep, sorry, Jonathan. Adding 4 each time. We said, what is repetitive addition? How do we rewrite when we add something a bunch of times? We literally, for lack of a better term, called it timesing in elementary school. Right? Because that's what we had. We had 4 a bunch of times. So we said 4 times what? Well, in this case, we don't know what we're going to be trying to find, the 5th, the 6th, the whatever term. So we say we're going to add 4 how many times?
N.
Very good. So we will write 4 times n. Again, see the difference between multiplying by 3, like we did on top, and adding by 4 on bottom. Multiplying a bunch of times, exponents. Adding a bunch of times, multiplication. And pick any one of those. What's your favorite? The first, second, third, fourth, or fifth term? All right. I'll choose the fourth. Let's check if we plug in 4 for n here and here to find our fourth term, then we know we should get this out. And what is 3 to the fourth? Well, you know 3 times 3 is 9, 3 times 3 is 9, and 9 times 9 is 81. There's your 4 3s. So that looks good so far. The negative is there. And plug in 4 here. What's 4 times 4?
16.
Looks like it holds true. If you wanted to check, you could check more, but I'm confident now that this is what they call the explicit formula to find the nth term of the given sequence. Patterns, patterns, patterns. Guys, this will get easier. All right? You just have to recognize these patterns and how to write certain things in certain ways. Okay? But there are formulas that cannot be written explicitly, but they still will have a pattern. Okay? I gave you an example down here, and then I'll go over what it's called. It's actually a famous one. Everybody see my set, my list, my sequence, we call it? It's 1, 1, 2, 3, 5, 8, 13, 21. Can anybody give me the next one? And give yourself a minute, see if you can figure it out. What is the pattern here?
34.
Ooh. Richard. Anybody agree?
Yep, 34.
Excellent. It would be 34. What would be the next one?
55.
The next one.
$89.
Good. I tested there a little bit, Kev. How did he get those so quickly? If you haven't seen the pattern yet, then you're like, where are they getting these random numbers from? Right? Because what we've seen so far is adding to get from one to the next, or multiplying to get from one to the next. But we haven't talked about is using things that are already there to get the next. Do you guys see what I mean? If I took the first two and added those, I get the next. If I took those two and added those, I get the next. Does anybody recognize this and know what it's called?
The Fibonacci sequence.
Ah, very good. Fibonacci sequence. And it may be 2 C's instead of 2 N's. I think it's 2 C's. I'll have to double check on the spelling. I apologize. But yes, it is the Fibonacci sequence. All right? And it's actually seen all throughout nature. You can look it up. It's actually in our book. They have a little short thing on it. But patterns come in all shapes and sizes, literally. And this is one that you can see in shells and their growth, leaves, all kinds of cool stuff in nature that Fibonacci noticed. All right? And these are called recursive. Recursive because some process keeps reoccurring. So how could we write the Fibonacci sequence if I wanted to find any one of these terms, the 12th term, what would I have to do to find the 12th term?
You'd have to know the 11th,
And
The 10th.
10th.
very good. I'd have to take these two things and add them together to find the next one. So how could we write that here?
A n minus 2 plus a n minus 1.
Excellent. Very good. And if we don't want to get so n minus 2, n minus 1, we also could have said to find a n plus 1, the next one, then you need to know the one before it and the one that you're at. I mean, same thing. All right. This is a little bit more easy to understand. You need the first two before it to find it, but sometimes they'll write it like this so that they don't have so many minus signs. Okay, to find the next one, you need the one that you have and the one before it. Okay, same thing, either way. So this is what is called a recursive formula, because what keeps reoccurring? To find any term, you will always do this. You will take the two before it, add them together to find the next. Right? And of course, these come in all forms. So here's an example. What if I gave you the first term and I told you how to find any term for n greater than or equal to 2? Now, why did they say this? Well, we already have the first. Okay, so if they ask you to write the first 5 terms, just like we started at the very beginning of today, I'm going to draw my 1, 2, 3, 4, 5 blanks that represent A1, A2, 4, and 5. And what do we already know? My first term is 2. And then what did they tell me to do? To find any term, I will take the one before it. To find any term, I'll take the one before it and do what to it?
Multiply it by 2.
First order of operations, very good, Brian. Double it, and then I'll add 1. Now, if you want to see it written out, I'll do it for a few. But to find a anything, it's 2 times a anything minus 1 plus 1. So to find our second term, which is what they said to let n equal, what does this say I need to know? My first term. And what is our first term? They gave it to us. It's 2. So it's literally telling you what to do for every single one of these. And once you understand that recurring pattern, then you just do it to find the next, then the next, then the next, then the next. So we are going to double the previous term and then add 1. So double the 2, we get what?
4.
Plus 1.
5.
Good. Now what are we going to do with that 5?
Multiply by 2.
To find the third term, I need to know the second term, which we just found is 5. So now we'll take that and double it and then add 1. So do you guys see why they call it recursive? That pattern is just going to keep reoccurring to find the next and the next and the next. So good, we'll take this and do what? double it, and then don't forget to add 1. So what do we get?
11.
11.
Good. Then what are we going to do with that?
Double it.
Now that I know the pattern, I'm just going to do it. I'm not going to sit here and keep plugging in all these ends. That's a waste of my time. We can do that till the end of time. I don't want to. Okay, I want to know the pattern, which they told us what it is. Take the term before the one you're trying to find and double it, and then add 1. So now I'll double this, which is what?
22.
Plus 1.
23.
Good. Now do what to that to get the last one that they wanted,
Double it and add 1.
which is
47.
on your side. That's right. That's it, guys. That's what is called a recursive. Those are much harder to go the other direction and come up with the formula for obvious reasons. Okay, so that usually doesn't occur, but these recursive formulas, they will give us and ask us to come up with however many terms. Okay, so the last topic for this first section, and then we'll jam into the last 2 sections, be a lot easier, is definitely something that you've seen, but maybe not just in math. Okay, if I wrote down this, sorry, what does that mean? Does it mean 5? No, sorry, I always like to do that in class, and whoever's in the first row that's not really paying attention, they always throw up their hands or get scared. But
Yeah.
I may have even got Richard or his children. I just woke up from taking a nap. All right, but 5 factorial is what we call this. And it doesn't mean we are just so excited and we said, hi, 5. All right. It literally is a way, a symbol for us to do something that we ended up having to do over and over again. Okay. So the symbol that they chose to represent this process is the exclamation point. All right. And there's a story about where that came from, and it was a typewriter back then, and guys like that symbol. He was limited. All right. And this is what they came up with. What 5 factorial means is you take whatever that number is and every integer on down to 1, and you multiply them. Okay, that's what factorial means. And so when we're dealing with permutations and combinations, some other things that you guys may be familiar with from high school, all right? When we were drawing blanks and trying to figure out how many different ways that we could make a pizza or order the classmates in line, whatever it might be, right? This came up a lot. And so instead of having to draw 30 blanks and do 30 times 29 times 28 times 27, we said, let's just make up a symbol to represent that, so we could just punch it in our calculator, have it do all of that. So if you haven't looked before, take a look. It's in your calculator. You will be able to just punch that in, and it'll give you the 120. Now, do you need a calculator to do 5 factorial? No. You know that's 20, you know that's 6, and you don't need the 1, so then that gives you 120. All right? But what we want to make sure that we actually know how to work with these things. So here's a quick example. And if you're going to use your calculator, you got to be very careful, because you know calculators don't make mistakes. You do. All right? So what am I going to put in my calculator, or what could I write out for this? Well, I know 12 factorial means 12 times 11 times 10 times 9 times 8. I'm not going to write all that out. But on bottom, I have 4 factorial times 6 factorial. Does that mean I have 24 factorial? No, Does that mean I get to add them and have 10 factorial? No. What you have is 4 times 3 times 2 times 1 times 6, 5, 4, 3, 2, and 1. Okay, that's not equivalent to 10 or definitely not 24 factorial. Okay, so what I always prefer you to do is, we know what that symbol means. And remember, the only time that we can cancel things is when we're multiplying, and since these are, we can. And since this is bigger than that, I'm going to cancel as much as I can from the top. So I know I'm still going to have the 12 times 11, 10, 9, 8, 7. But guess what's going to happen to the 6, 5, 4, 3, 2, 1? Because we're multiplying, it's going to cancel with that 6, 5, 4, 3, 2, 1. So I'm only going to be left with the 7. The 6, 5, 4, 3, 2, 1 all canceled out with that 6, 5, 4, 3, 2, 1. But I still have what on bottom? The 4 times 3 times 2. Which means I can do some canceling because we're multiplying. This 12 with that 12. This 2, I'm not going to do it with the 10 because I like multiplying with 10. I'd rather do it to the 8 here, which would give me a 4. And so if I had to do it by hand, that's what I would do. And I would multiply whatever's left, which 4 times 9 is 36, times the 10 is 360, times the 7 and 11, which is 77. Otherwise, you can find the factorial in your calculator, and it will do a lot of that work for you. Just be careful you input this with parentheses. Otherwise, your calculator will do what you say, and they will put 12 factorial, then divided by this. Then it will take that, and it will multiply it by 6 factorial, because that's what you're going to put. Okay, make sure you put parentheses around this so it does all of that and divides it into the top. All right, anybody get an answer for me? $27,720. Just in case you're doing it on your calculators. Okay, so the factorials will come into play a little bit here, so wanted to make sure that I went over that. Otherwise, we're going to move on to 13.2 and 13.3, which hopefully won't take me too long so we can get to our group quizzes. All right, so I haven't said what this is titled yet because, as you can see, my very first thing I'm going to ask you is, how do you say that word? What are most of you going to say?
Arithmetic?
Ooh, close, Richard. Most people read it as arithmetic because that's what they're used to seeing or hearing from elementary school. But it's actually closer to what Rich said. It's arithmetic. Okay, that's our fancy way of letting you know that we're just going to be using arithmetic. And what is arithmetic? What does that mean to you, arithmetic?
Order of operations.
Good, that's one thing for sure. Get even more basic.
Addition and subtraction.
Yeah. Adding and subtracting. And if we're using what are called arithmetic sequences or arithmetic with our lists, guess what we're going to classify these as using to get from one to the next to the next to the next? We're going to be using arithmetic, you guys. Okay? So an arithmetic sequence is to get from one to the next, we will add or subtract some, what we're going to call common difference. Okay? That common difference, we're going to use little d, lowercase d for that. If I give you the first term, I tell you A1 is, let's pick a number, 5. And I tell you the common difference is 2. Or 3. Or negative 3. Then could you give me the first 5 terms? Well, definitely, what's the first? But what did I tell you the common difference is for this arithmetic sequence? Which means, how would I get to the next?
Add the -3 to the 5.
Very good. And instead of saying add a negative, isn't that the same as just subtracting? Very good, Emily. You're just reading it as they wrote it down. Perfect. Adding a -3 is the same as subtracting, so what's 5 minus 3?
According to my calculator, it's 2.
Yeah, in my calculator. Get out of here, Richard. Then what do I do when I subtract 3? To that.
-1.
Beep, boop, 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 boop. Now careful, -1. Very good. Subtract 3 to that.
-4.
And that pattern continues. So unlike the first section, where it was a little bit more daunting to figure out how we went from one to the next, these are nice. We like these. Because what are we only going to be using? Arithmetic. Adding the same number or subtracting the same number to get from one to the next. It's that easy. Which means, could you tell me what's happening to this? Can you give me that general term? What did we say would happen each and every one of these? Well, it's going to be subtracted by 3. And what did we say happens when we add or subtract the same number a bunch of times? What did we call it?
A sequence?
Careful, John, we called it multiplying. Okay? The sequence is the list that I gave you here. But when you add or subtract by that -3 a bunch of times, well then I'm going to do it n times. And I know if I put in a 1 here, a 2 here, a 3, a so on, I should get those values, shouldn't I? The problem is when I put in 1 here, what do I get? I get a -3. What do I need in order to get a 5? What would I have to do to this to get it all the way back up to the 5? I definitely have to add, and I'd have to add what number?
8.
Well, if I did that to every single one of these, do you think that that would work? It worked for the first one. Would it work for the second? Plug in a 2 right here. What's a -3 times 2?
-6.
Plus 8.
2.
Hey. Let's test this one. Let's go all the way over here. Plug in a 5. What's a -3 times 5?
-15.
Add 8. Sweet. We just came up with the explicit formula, that generic form for that scenario. So if I'm adding or subtracting any number of times, we'll always just start with that. And all we have to do to find that first term is see what we would get when we plug in 1 and then get there. And in this case, we had to add 8 to get to that 5. And that will work every single time, my friends. That's the good news. Okay? Even better news, if you don't quite understand that, you guys look, they have a formula. They have a formula for you that will always work. And it says all you got to do is to find any term, you need to know the first term and the common difference. And so they gave me the first term was 5, plus we're going to do n minus 1 times that d, because 5, I had to do 1, 2, 3, 4 of those common differences d to get to that fifth term. So that's why it's n minus 1. And I said that the d common difference was -3. Now, of course, we have our an with the n in it, just like we did here. But now we got to go through and distribute and clean this all up, where if you just look at this and give me that, I'm good. Get there as fast as you can. That's my goal. So now I'd have to do this, and I'd have to distribute. So I got my 5 still. That would be a -3n, and then that would be a +3. And what do you notice? We can still combine. The -3n is there, but the 5 plus 3 gives me the 8. Just like we got there. Okay, so make sure if you're not taking notes, haven't been yet, that you write this down. And when's the only time that we can use that formula?
With an arithmetic sequence.
That's right, Ant. If it's an arithmetic sequence, meaning they added or subtracted to get from one to the next. And of course, we can have recursive formulas and not just our explicit one. Okay, it's the same thing here. Wanted to highlight it for you. A recursive formula, meaning as long as you know the previous one, you can add the common difference to get the next. Big deal. Not nearly as difficult as the first section. Okay, so we won't be doing a lot of recursives, more the explicit formulas. So make sure that you have this one written down. Okay, how can you always find that common difference? Take any two, doesn't have to be the first two, take any two and take the result and subtract the previous, and that will give you the difference, that common difference for each one of those. All right, there it is again, just trying to make sure that you guys have it. All right, let's do an example. What if I gave you that? Can you write the explicit formula? Well, if you want to use the formula that I highlighted several times, go for it. Otherwise, I'm cool with you guys just writing it down using your mind instead. As long as you know the pattern, which would be what?
-3.
Subtract 3.
They're subtracting 3. I should have chose a better example in mind, right? But they're doing -3. How many times?
N.
Any number of times, that's right. But if I plugged in a 1, I would be at what?
-3.
I'm going to have to add a whole lot to get back to my 50 that I need to start at. And how much?
It's 3.
Done. Now, if you don't want to do that, you can always take the A1 and the common difference, plug them in, distribute, do your multiplication, and you will also eventually get there. That just requires a little bit more work. This requires a little bit more thinking. I'm fine with either way. I just like to give you guys options. Okay, much easier than that first section. Okay, so another thing that they'll ask us to do is take this, which what kind of sequence is this?
An arithmetic.
It is arithmetic. How do you know?
Honestly, I read it on the screen.
Good. It's arithmetic. How can we tell if it's adding or subtracting the same number to get from one to the next? And Richard, as you mentioned earlier, they have to give us at least 3 to see that pattern. Okay? Why is it finite since you're reading things off the screen? Why is it finite arithmetic, even though it has the ...
Because the last number is 56, so it ends in 56, I'm assuming.
Very good. Excellent. So I know that this is my first term, this is my second, this is my third, and then this is my nth. And what do they want us to figure out?
How many terms there are in?
We need to therefore, very good, Brianna, solve for that n. If only there were an equation that I knew everything but one thing in, gosh, that would be great, wouldn't it? Oh, wait, Richard, you just told me it's arithmetic, and I highlighted several different times that this formula can be used on any arithmetic. And do you see how many unknowns there are? 1, 2, 3, 4. And of those 4, I need to know what?
3.
That's correct. Do I have this, this, and this so that I can find the number of terms? Well, obviously I have the first. Obviously we just found the common difference. So I have these two for sure. Do I have the a sub n so that I can find the n?
Yes.
And that's why I like to label things. Because yes, you can see that I have that, and this is my common difference. So very good. I will go here and I will substitute in everything that I know, and I will leave the one and only thing that I need to know. A1 is what? Our common difference is what?
5.
And that could be positive, could be negative, so very good, be careful with that. And then the one that's a little weird, that is even the reason I'm going over this, is a sub n. That is what?
$56.
That's the 56. And notice, guys, just like we talked about last unit when we were doing the systems of equations, ultimately the only thing I know how to solve is one equation with one unknown. Now I should be able to solve for that n. Does that make sense?
Yeah.
All right, then you guys should be able to finish. I'm going to do 2 steps in one if you guys can handle it. I'm going to subtract the 6 over and multiply through to get my 5n minus 5. That then cancels out. And on the other side of my equal sign, I now have 56 minus 6, which is 50. Add the 5 over, we're on our way. We now have 5n equals 55. And 5 times what gives us 55?
11.
That's it. We know that this would have been the 11th term. Now you guys will be surprised that, or you might not be, people will sit here and actually add 5 all the way until they get to 56. And they'll try to count how many. Don't make me on the quiz or test give you a much larger one, like 256, just so that you don't do that. Okay? Use the formulas, use the equations, use your mind. That's why you're in college, right? Is to expand that thing and learn how to use it differently and better. Okay? That's it for 13.2. Last thing, 13.3. Geometric sequences. So remember 13.2 was arithmetic, where we used arithmetic, adding and subtracting to get from one to the next. It had that thing we called the constant difference. Well, what do you think geometric represents?
Constant ratios.
Very good. Geometric is then going to be using multiplication and division. Okay? And what do you prefer? Do you like adding or subtracting better? Most people would say adding, right? So what do you prefer, multiplying or dividing better?
Multiplying.
Yeah, so we're going to actually say, you know what? Forget division. We're just going to concentrate on multiplying. But what if you wanted to, you know, divide by 2 every time? What would you have to do if I had this list?
Multiply by 1/2.
Yeah, very good. We could say that there is a constant ratio of 1/2. That's the same as dividing by 2. So that we don't have to deal with division and we can just deal with multiplying only, we will use R as our constant ratio instead of D for our constant difference. Okay, and that is the difference between arithmetic and geometric. Otherwise, everything is basically the same, other than, of course, our formula. The formula for this one is that. Make sure that you have this one down as well. And notice it has exponents. Why does it have exponents? What are we going to do in order to get from one to the next?
Multiply.
Multiply. And when we multiply by the same thing a bunch of times, we know that that means we're going to have that thing to the end. Okay, but remember, that's just my R. We're also going to need to make sure that we get back to our original. So sometimes we're going to have to multiply by that first thing. Okay. So that is the formula that we are going to also memorize. And what I like to do is always put parentheses around that and or that. It's A1 times R to the n minus 1. So if I'm telling you A2 and A3, what should you be able to find from the second to the third term? Anybody?
The
The
common
ratio.
difference.
Very good. Now careful. Somebody said common difference. Somebody said the ratio. Which one is it?
The ratio.
How do you know? It's geo. Ratio. If it's arithmetic, you're going to use arithmetic, adding or subtracting. There will be a common difference, added or subtracted to each one. The geometrics are going to have that ratio for geo. And so what would we do to get from 4 to 32?
Multiply by 8.
Which means if I know this formula, A sub n equals A1 times R to the n minus 1, we just found the R to be what? 8. Could we therefore figure out what A1 would be? Well, if we multiply by 8 to get from one to the next, moving left to right, what will we have to do to go backwards?
Divide by 8.
Very good. And so take this and divide it by 8, and that will get you.
1/2.
And just to make sure, let's double check. Does that still hold true? If I multiply by 8, what's half of 8?
4.
Good. Multiply that by 8, we get 32. Do it again and again, and you eventually could get here. But remember, we're not doing this to be able to just boom, boom, boom in our calculator. We want to make sure that we can use this formula to find A36. So we now know that A1 is 1/2, and the n that we want is A6. Now careful guys, this is where most people make mistakes. Can I take half of 8 right now?
No.
No, remember we do not multiply before we deal with the exponents. That's that parentheses, exponents, multiply, divide, add, subtract, order of operations that Richard had mentioned. Okay, so you're actually going to need a calculator, and you're going to have to know how to use it well, because we're going to have to take 8 and raise it to the 5th in your calculator, which there's often an X to the Y button. Okay, use that in your calculator and hit 8 to the 5th and then divide it by 2, cut it in half. So 8 I would raise to the 5th and then divide that by 2 or multiply it by half. And you get 16,384. And I'm fine with you guys not putting commas on those because we already have commas to break up our terms in this sequence. All right, so let's see if you guys can put it all together. Let's see if you can go the other direction. Let me give you a geometric sequence or list of numbers, and can you give me the formula? What's the nice thing about this formula? What are the only 2 things you need to know in it?
A1 and R.
Yep, that's it. Just like in the other one, it was A1 and D, the common difference. What obviously do you already know?
A1.
They flat out gave it to us. What's the only thing you have to come up with?
R.
Where are all my pirates at? Thank you, Brianna. The R. And what is my R on this one? Careful.
-3.
Good. We are multiplying by that -3. And again, can I just take this negative and multiply it times that and just say it's 3 to the n minus 1?
No.
Very good, because we don't know what the exponent is. And we have to do that before we multiply. So guess what? You're done. It's that easy. Please don't make it harder than it is. Okay? So that's it for this week. Hopefully you guys understood everything that I covered. I went really slow at the beginning because those are a little bit more difficult. We're introducing a lot of terminology, but once we get to the arithmetic and geometric, we have formulas to use. We can just use those. They're just going to give us different looks on what they're giving us and what they're asking. All right? Hopefully that made sense for you. I'm going to go ahead and stop the recording now.